My name is Scott Sanderson, and the title of this talk is Hosting Notebooks for 100,000 Users. You can find me online at these various places. So I'm S. Sanderson on GitHub, Scott B. Sanderson on Twitter. The slides will be posted to ssanderson/JupyterCon 2017, but if you go there right now, you're going to get an empty GitHub repo, so don't try to follow along with the talk. And I work for Quantopian, so a little bit about Quantopian. Quantopian is a platform where people can come together as a community and write algorithmic trading strategies in Python in the browser. So we provide a hosted research platform and a backtesting API and all sorts of different kinds of data sets for people to write, test, and develop trading algorithms. So the outline for this talk, we're actually going to start with a demo of the thing that we're going to be talking about building, so we have a sense of sort of what we're trying to get to and what the goal is. Then we're going to sort of take a step back and talk about sort of what the goals and challenges were of the project that I'm going to be talking about today. And then we're going to talk about the different ways that Quantopian extends or modifies or otherwise sort of mucks with the standard behavior of the Jupyter Notebook in order to support the kinds of workloads and the kind of use cases that we're interested in. So in particular, a couple things we're going to look at is how Quantopian manages user identity for its Jupyter Notebook deployment, how we deal with notebook storage, dealing with potentially multiple Jupyter hubs in order to scale out to the number of users we want to support, and finally, how we allow users to share notebooks with one another. So to start off, we're going to do a demo. So this is the Quantopian website. So if you just type in quantopian.com and you're logged in, you'll get dropped here, which is the community page. So this is a place where people can share and discuss and talk about the trading algorithms they've written. If you switch over to algorithms, this sort of takes you to the place where you actually work on the logic for your trading strategies. This is what sort of Quantopian looked like, or this is what all of Quantopian development looked like at the start of this project. So we had this IDE. It's built on CodeMirror, which is the same text editor that Jupyter is built on top of. And you can write sort of the logic for your trading strategy on the left-hand side, and then you can set some parameters for it on the right-hand side, and you can run backtests. So this is sort of the simplest possible hello world algorithm. So we have an initialize function that doesn't do anything, and then we have a handle data function that's going to get called once every minute. So this algorithm is just going to order a share of Apple every minute. And if I hit run backtest or build algorithm and the conference Wi-Fi gods are being kind to me, we may see some progress here eventually, but I'm not going to hold that up for too long. At some point, we may eventually see things happen. Anyway, so circa sort of early 2014, this was kind of the state of the platform. And we had this place where you could come in and write the logic of a trading strategy. So if you had a trading strategy in mind, this was sort of a really good place to come and write your backtest. So the problem with that is most of the time that you want to spend developing a trading strategy isn't writing the logic for your trading strategy, right? The hard part of writing an algorithm isn't writing the algorithm. It's researching the ideas behind the algorithm, right? It's looking through data, visualizing data, trying to understand patterns and trends in data, and trying to develop some thesis about how the market works that you can then exploit in a trading algorithm. And that's sort of where most of the interesting novel work happens. And then when you finally have an idea that you think is validated that you want to test, at that point you want to take it and actually put it inside a trading algorithm. So what we found, circa early 2014, is that we had users that were giving us these kind of strange feature requests. So things like, I want my trading algorithm to be able to plot data, or I want my trading algorithm to be able to stop and let me inspect all the values so that I can do an interactive analysis from inside my algorithm. And initially we were like, that's kind of strange. That's not sort of what the point of an online trading algorithm was. And what we eventually realized was that people, what they wanted was Jupyter. They wanted some way to interactively explore the data that was available on the platform. So they wanted to be able to explore and visualize data, test their hypotheses, analyze the results of their backtests, all these things that we sort of think of as interactive data science tasks, which are the things that Jupyter is a really great environment for. And so what we wanted to do was somehow integrate Jupyter to the platform. So a couple of the interesting challenges that we had as a result of that is we already had this large website that was built around this IDE, so we needed to somehow take Jupyter and embed it or make it a part of that existing application. We wanted to support pretty large user base. So Quantopian, I think, has north of, I don't know what our last announced number, but somewhere on the order of like 120,000 registered users. And so that's quite a large notebook deployment, and we wanted to be able to allow all of those people, or at least the subset of those people who are online at any given time, to do their analyses. And the kinds of analyses they want to do are pretty resource intensive. So that was going to be sort of an interesting challenge for us. And then another important goal for us was that a big part of Quantopian is the community aspect of it, right? That you can share and talk about and discuss your algorithms and trade ideas with people. And so we wanted to have some robust support for sharing and using the notebook to interact with other Quantopian users. Right, so just to sort of repeat some of the things I just talked about. So financial analyses generally are pretty RAM and CPU intensive. So trying to scale to support the kinds of workloads that we wanted to support for the numbers of users we wanted to support was going to be a pretty big challenge. And it pretty much mandates that we have to be somehow spreading users across some reasonably large number of servers. We also, we're a website that's up 24 hours a day. We're not, a small research lab where we can take the server down for an hour when everyone's at lunch. We want to be able basically be up all the time. So, if you're a Quantopian user and one of those servers fails, you shouldn't lose your work. Or you shouldn't have to, wait for 10 minutes when we deploy an upgrade. Or you're also a random stranger on the internet to us, so you shouldn't be able to, say, take down the resources that another user is using, or you shouldn't be able to intercept their work. So we need to make sure that users are somehow isolated from one another in this way. And then, so those two things are sort of kind of, standard challenges for scaling any kind of service. And the easiest way to scale some web service, if you have sort of a standard, HTTP server, is you make everything stateless and you just say, here's my server, it does a thing, and I don't care which server my request goes to. I'm just going to make as many of those servers as I need to service the load that you have. And that works great as long as your requests are stateless, right? That I don't care which server I'm talking to at any given time. And that's not the case for Jupyter, because Jupyter is sort of inherently about maintaining these persistent processes that we talk to for extended periods of time, and maintaining these notebook documents that we author and share and collaborate on and edit over time. So state is sort of inextricably bound up in the kinds of work that we want to do with Jupyter. And so that sort of gives us some unique challenges for trying to scale this problem in a way that we might want to scale other kinds of web services. And just another aspect of state that we might not normally think about is that user identity is another sort of form of state that we care about in this system. On a Unix server, on a traditional server, you might have a login to that server where you can SSH to that, or you can somehow log into the box. We don't really want to give Unix logins to 100,000 users, so we need some way of managing a persistent identity. And that also goes back to things like maintaining your notebooks and associating those notebooks with a persistent user identity. So with that sort of background in mind, I'm going to do a super quick introduction to the architecture of the Jupyter Notebook, and then to Jupyter Hub, which is a multi-user notebook server. If you're interested in that in more detail, there's going to be a talk from Min and a bunch of other folks this afternoon, sort of going in depth about Jupyter Hub. But this is just going to be sort of enough to get you up to speed for the things we're going to talk about. So this is the single-user Jupyter Notebook server. So this is the process that comes up when you type Jupyter Notebook. This slide is shamelessly stolen from Carol Willing's talk from Jupyter Days Atlanta, I think. So basically, the Jupyter Notebook is a server. You talk to it with a browser, the same way you talk to most websites. And that server connects to the browser via WebSocket, so you can send messages back and forth. And then when you open up a notebook, the server creates a kernel, which is a process that has some running interpreter, and it associates that kernel with your notebook. So you're sending messages which are things like snippets of JSON, or the code that you want to execute, or commands going to and from a widget. And the notebook server's responsibility is essentially to route those messages to the appropriate kernel, let that kernel respond to them, and then route the messages back to you. So we can think of this whole sort of single thing as one single user server. And one important thing about this is that the server doesn't really have a notion of a user. It has a notion of authentication. So I might have to know some secret or have some information in order to log into this server, but this server has no notion that I'm Scott and that I have particular login credentials associated with Scott. So the project that solves that problem is Jupyter Hub. So the Jupyter Hub is this project that essentially tries to aggregate lots of little Jupyter clusters. So it's primarily composed of 3 pieces. So it has some notion of who users are and how they authenticate. It has a notion of spawning those single user servers for those users. So if I, Scott, try to connect to the hub says, yes, you're Scott, I've authenticated with you, and then it will create a server for me if I don't already have one, and then it will persistently route my connections to and from that server. And then it can route me back and forth there. And the important thing is that it provides this sort of single entry point. So the browser, when you're using the Jupyter Hub, doesn't talk to the individual notebook servers directly. It talks to a proxy that sits in front of those servers. And the hub's responsibility is essentially to manage the configuration of that proxy by making sure that users are authenticated and that proxy knows how to route people around. So here's just sort of another diagram of that. So we've got various humans drawn in XKCD style. They're all talking to the configurable HTTP proxy. We have various notebook servers, often sort of one for each user that we're talking to. And the proxy knows how to route messages back and forth between users and those servers. And then there's a centralized hub that manages a couple pieces of state about those users and manages authentication of those users. So it sounds like sort of at the start of it, like the hub solves a lot of the problems that we're interested in, right? It has some notion of user identity. It has some notion of spawning all these different servers. And maybe we could think about spawning those servers across different machines. And it sort of gives us this single point of entry, which is an important thing for us. We don't want each individual user to have to go to a different URL or something like that. So let's sort of look at some of the case studies for those kinds of problems that we wanted to solve. So the first one is user identity. The default Jupyter Hub architecture authenticates via Unix username and password. So that's bad news for us because we said we don't want to give all of our users a Unix login. We do have some good news, which is that we do already have a login system, right? Quantopian already has some notion of who you are. So all we really need to be able to do is somehow get that information to the Jupyter Hub. And so even better news for us is that the Jupyter Hub authentication mechanism is pluggable, right? So Jupyter Hub defines this interface, which is an authenticator. So you can, as an administrator or as a consumer of Jupyter Hub's APIs, you can subclass this authenticator class. And the simplest possible version of that is you just have to implement this authenticate method, which takes some information about the current request that's being made. In particular, we often have like a username and a password. And so this is sort of the simplest possible implementation of an authenticator, which just takes a dictionary from username to password. And when a user tries to log in, it checks if that username is in the dictionary and it matches the password. And if so, it logs them in. So what we want to do is have some authenticator implementation that knows about Quantopian and knows about users' sort of Quantopian identities. And there's a fairly common and well-established protocol for having one website authenticate or provide information about another, about its users, which is OAuth, or it was open authentication or omni authentication. So we can just make Quantopian an OAuth provider and then use OAuth to identify or to authenticate our users. So the authenticator is a little bit more complex than this dictionary auth. This fits on a slide. The authenticator is maybe 200 or 300 lines of Python, but it's still relatively compact. So basically the way that OAuth works is when you come to Quantopian, you try to log into the research environment, you actually get redirected to a Quantopian URL. So your browser goes away from research, goes to some Quantopian page. And the important thing is, the reason that it's a Quantopian page is important is that you're already authenticated with Quantopian and you have cookies that the Quantopian front end can use to verify that you are who you claim to be. And if that succeeds, then the front end redirects you back to, so authorized ensures that we're logged into Quantopian, and then it redirects us back to the hub with some additional information that we can then use to talk to the front end again to ask who you are. So the front end redirects you to this OAuth callback. The OAuth callback sends the information back to the front end. Front end responds with an access token. Then we send that access token back to the front end. So OAuth is kind of this complicated back and forth dance. We finally send that to the API, and the API says, yes, you were in fact Scott, and then all is good. Some sort of reflections on that API. So OAuth kind of feels like overkill for this use case, right? It's like, I got a token, then I exchanged that token for a code, and then I exchanged that token for a resource ID, and then finally I used that resource ID to log in. So if we were like designing an authenticated mechanism from scratch, probably this isn't what we would use, but OAuth is sort of so pervasive and so well supported across various different projects that it's still a nice standard to use. And it means that you can do something very similar to what we did and authenticate with GitHub usernames or with Google usernames or Facebook usernames. Basically any site that you ever see on the internet that authenticates, that allows you to authenticate via some other login is using this protocol. So even though it's a little bit clunky for this case, it's nice to use this sort of well-supported protocol. So yeah, OAuth is standard and widely available, and there's lots of good open source libraries for doing it. Another problem, this is probably the kind of the thorniest problem that we thought we were going to have to deal with initially is notebook storage, right? So the standard Jupyter Notebook interface provides this sort of file system interface for storing notebooks, right? So I have this browser, and I can navigate up and down in this hierarchy of directories, and it sort of presents the illusion that I'm interacting with a file system. And in fact, in sort of the standard Jupyter Notebook implementation, that's a pretty transparent pass-through to the file system. But even though it's just sort of passing those operations through to the file system, it actually abstracts those operations behind this thing called the Contents API. And so the Contents API essentially implements all the operations that you'd want to do on files, so saving and deleting and loading them, and translates them into HTTP verbs. So in the browser, we can click on a notebook and open it, or we can delete it, or we can save it. And what the browser is going to do is translate that into an HTTP request. So when you load a notebook, you make a GET request. When you save a notebook, you make a POST request. When you delete a notebook, you make a delete request. And then there's a couple extra endpoints for doing things like saving and restoring checkpoints. So IPython or Jupyter has this notion of I'm going to save sort of a provisional copy of my notebook that I can restore to at a later date. And the Contents API works with these sort of abstracted entities that are representations of notebooks or files, which we call models. And you can see that this contains things like your path and the name and the MIME types, like what kind of data you carry, when you were created, when you were destroyed, and then this content field, which contains sort of the meat of the stuff. So we have metadata, which is various kinds of extensions use metadata to put extra information in the notebook. And then finally, we have cells, which is sort of the piece of JSON that we tend to think of as the notebook itself. So the Notebook API is sort of, or the Jupyter Notebook server, the standard server, implements this HTTP API, and it implements it by dispatching to a Python API, which is called a Contents Manager. And the default implementation is called File Contents Manager, and it does more or less what you'd expect. So if you say save a notebook, it writes the notebook to a file system. If you say delete a notebook, it deletes the notebook from the file system. If you say load it, it reads it from the file system. But like the authenticator in Jupyter Hub, the Contents Manager class is configurable. So I can come and write my own implementation of the Contents Manager, and as long as I've implemented the interface correctly, I can sort of transparently change out what it means to store a notebook, or what it means to load a notebook, or what it means to delete a notebook without the user interface, or without sort of the user's experience of the application ever changing. So sort of a minimal complete definition of a Contents Manager is 6 or 7 methods. So it's a little more complex than an authenticator, but not a whole lot more complex. So we have to be able to get things, save things, delete things, rename things, check if files and directories exist, and we have to be able to know if things are hidden. And so we looked at that and we said, well, maintaining state is a really hard problem. And trying to have this fleet of servers with notebooks all living on the file system sounds like a nightmare, especially if like a server fails, we have to back them up or we have to try to recover them. There's things like NFS that we could use to mount network file systems, but then we have to have some sort of permissioning system for managing all those things. In general, sort of state is this really thorny problem when you're trying to scale a system. But there are applications that we've been using for 50, 60 years that are really, really good at managing state, and they're called databases. So what we did is we said, okay, we've got databases. We know how to use databases. Databases are really good at managing state. Instead of managing the state of our notebooks on our servers, on our notebook servers, we're going to delegate that problem to someone else who's better at managing state than we are. And so we wrote this library called PG Contents, which is a drop-in replacement for the standard file system-based Contents API, except that it stores notebooks in PostgreSQL instead of on the file system. So I'm going to do a brief mini demo of PG Contents. If I can figure out how to get out of here. There we go. So here I've got a Jupyter Notebook server running. And for all the world, this looks like a normal Jupyter Notebook server. I can open up cells, I can execute cells. I can modify cells, and as a user, this is just like a normal Jupyter Notebook session. And I can have directories, and I can rename those directories and move things around in them and do all the sort of file system-y things that I like to do as a Jupyter Notebook user. However, if we look at how I started that notebook session, we pointed it at this fancy config file, and if I do Emacs on that file, then we can see that that config file is actually telling the Jupyter Notebook to use a different contents manager than it would normally use. So we're saying from PG contents import Postgres contents manager, and then we're telling the notebook app that it should use that as its contents manager class instead of the normal file system contents manager. And then we have to tell it a bunch of extra information. So we have to give it a URL to connect to a database. And we can give it some things like a user ID. So another challenge that we have is we want to store things on the file system. Multiple users might have the same database or might have the same notebook with the same name. We need to somehow namespace those. So we can give each user their own unique namespace of files. And then if we're storing things in a database, we probably want to do things like make sure that there's some maximum size that we can put on those files so that a user doesn't try to insert like a 5,000 gigabyte file into the database. And there's some other options that I can do in here as well. So we can do things like adding configuration to encrypt notebooks at rest in the database, for example, is an important thing for us for maintaining the security of those databases. So I restart that. And then we can take a look at that database that we're pointing at. So down here, I'm just in a Postgres REPL. So if I do, from pg tense.files import, select star from pg contents.files limit 1. Right, so we say this is a file. So it's got an ID, it's got a name, it's got a parent name, and then it's got some content, which is this giant binary string, which is a Postgres byte A column, which is basically just arbitrary binary blobs. It initially sort of sounds a little bit strange to be storing these like giant blobs of binary data in a relational database. Postgres is actually really, really good at storing this kind of data because it has this system called Toast, which is the large large object storage system. And basically what it means is that Postgres doesn't actually store this giant blob of binary data in line in the tuple in the database. It stores it out in a separate storage location and then just maintains a pointer to it. I sort of worked on this and like implemented this as an initial implementation and thought like, okay, we'll have to replace it with something real eventually. And then we're like, this just works. So it's been great for us. And I can do, add a couple more of those. So we can see also things like we can preserve the parent structure and we can query for things in a directory and all that sort of thing. So that's PG contents. So a couple of features of that we just went over. So it's fully API compatible with the default contents manager. The way that we test PG contents is we actually import the test suite from the original notebook and subclass it and make it use our contents manager instead of the file contents manager, and then verify that it passes the exact same test suite. Which is a really cool way, I think, of testing that something is a drop-in replacement for it, is to say, if I'm a drop-in replacement, I should pass your test suite. It allows us to have separate namespaces per user. It allows us to do multiple checkpoints per notebook. So one of the things that the default contents manager doesn't do is it only gives you one checkpoint for a notebook. So PG contents actually maintains the history of all your notebooks, and you can revert back to arbitrary different states. It has a configurable maximum file size. And it has optional encryption at rest for notebooks via the cryptography package. Oh, and it also has the ability to actually combine file systems in Postgres via this thing called a hybrid contents manager. So I can have a directory that's mostly managed by Postgres, except this one subdirectory that I actually want to be on the file system. So some vanity metrics, because everyone loves vanity metrics. We added this 4 or 5 years into the site's existence. So not all of those 100,000 registered users are actually, have stuck around for the entire lifetime. So we've got about 65,000 users have created a notebook. We've got about 220,000 total notebooks. We've got about 310,000 total checkpoints. We're about 450 gigabytes of notebooks stored in that database. So like I said, Postgres is doing a really good job just storing all this binary data for us. So some scaling issues. There actually have been surprisingly few. I've been generally very impressed with Postgres' ability to handle this workload. The most significant issue we ran into was running out of database connections. So each open connection that you have to a Postgres database consumes some RAM in the database. And if you have hundreds or thousands of those open at a given time, the database starts to complain. There's already really good, robust tooling for this. So PG Bouncer lets you sort of transparently pool connections because they're generally not all in use at once. So basically, notebook clients connect to PG Bouncer maintains a pool of connections, and then it sort of muxes all the different connections back and forth to the actual database. So that's PG Contents. So that one thing that's nice about that, right, is that PG Contents solves one of the really thorny problems for us, which is how are we going to manage the file system state of all of these notebooks, right? So users have all of this stuff. They might expect them to be on the file system, and one of the things that would be entailed by that is that if I as a user come to Quantopian and then I go away and then I come back a week later, if we were storing stuff on the file system, we'd either have to be synchronizing notebooks across all of our different servers, which then becomes hard if we have an outage or if a server goes down or we have a hardware failure, or we have to be persistently routing the same users to the same hubs, which then means like it's hard for us to do rolling restarts, it's hard for us to migrate people. There's all kinds of problems that come out if we have to keep people on the same server at the same time. But one of the nice things about not having persistent state on the server that we care about anymore is we can sort of route people around to different servers however we want. Now, within a given notebook session, like your connections are obviously going to a persistent kernel because you have a process running that you're talking to. But if you're working on a notebook and you leave and you come back a day later, I can route you to a different server and you're going to be none the wiser. And so one of the things that makes us really want to be able to do is run multiple hubs, right? Because the hub has the ability to sort of be one single point of entry and then fan out to servers or to notebook servers that are maybe running on different servers. But that still gives you a single point of failure if that hub node goes down. And so one of the things we wanted to be able to do is say, we're not going to worry about trying to make that node triply redundant and super duper robust. We're going to say, servers should be expendable. If that server dies, it dies. We're going to be like, Drago and Rocky, where it's just, if it dies, whatever, we're going to throw it away and make a new one. So what that means is that we want to be able to have multiple Jupyter Hub instances. We want to route people to those hubs. I'm going to claim that the Jupyter projects, as they've evolved in time, are a tower of increasingly elaborate lies. And what I mean by that is that all of the Jupyter projects, in some sense, sort of present the illusion of talking directly to a kernel, and they add more and more layers of indirection as they go. So, in the beginning, there was just IPython, and IPython mostly didn't lie to you, right? You're talking to a kernel. The kernel, there's no like message passing. You're a process. You're talking to it over standard in. It's giving you answers over standard out. Kernel is nice. And then we move to the Jupyter console, and now suddenly there's a layer of interaction. So we can sort of spawn kernels asynchronously, and then we can connect to them via a terminal. And that means that I can do things like connect multiple terminals to the same kernel and have them sort of share state, or I can connect to a terminal or to a kernel and then detach from it for a while and then come back to it later. Right? The kernel lifetime is made separate from the lifetime of my interactive session. And what's nice about the console is that for the most part, when you're using it, it presents the illusion to us that we're just talking to a kernel. It's just a normal IPython shell. But behind the scenes, it's lying to us. And it's saying you're talking to a kernel. It's actually you're talking to a terminal who's sending messages to a kernel and sort of routing those messages back and forth. Then we come to the Jupyter Notebook. So the Jupyter Notebook, is adding more layers of indirection between us and the kernel. So now as a user, we're talking to a browser, which is talking to a server, which is routing those messages to the kernel. And now I might have multiple kernels and multiple notebooks, and it's sort of routing messages back and forth and making sure that all the notebooks and all the kernels line up and all the messages don't get crossed. So we're getting sort of increasingly far away, or increasingly many hops between the user and the kernel. Jupyter Hub adds another layer to this. So now we don't just have many notebooks and many kernels. We have that whole box taken and replicated many times again. So now we have many users using many browsers, all talking to one proxy, and then that proxy is routing those messages to servers. Servers are routing those messages to kernels, and all those messages make that all the way sort of back and forth along this hop as many times as we want. I claim that for this Quantopian project, what we really wanted was the illusion of having a single Jupyter hub, but with multiple real hubs. Another thing that we also wanted that we talked about is we wanted to somehow embed the hub in another web page, right? We don't want users to go to some other web page to do their research thing and then come back to Quantopian to do Quantopian things. We want it to feel like one large integrated project. And so I claim that we can sort of kill two birds with one stone by rendering the hub in an iframe. So this is sort of what the multi-hub picture looks like. So now we have users talking to browsers, talking to Quantopian, and then Quantopian is rendering a little sub-web page inside of itself, which is a Jupyter Hub instance, which is then routing me to a server, which is routing me to kernel. And again, we're sort of going all the way back up the tree. So to pop back out to Quantopian again, we'll see if I can actually get to research. This connection may be dead, but we'll see. All right, we're going to move on. Oh, maybe. Haha. Maybe. Notebooks with lots of images are not a good choice for conference Wi-Fi. Anyway, if we wait long enough, I promise you a notebook would show up here eventually. So the only point I want to make here is that basically everything below this black line is actually an iframe living inside of the main Quantopian website, and then everything above this black line is the Quantopian website. So we're basically embedding the hub directly into a page, and one of the things that means is that when we go to load this page, the top level application can say, all right, which hub am I going to route this user to? And I can make sure that I route you persistently to the right hub if you come back multiple times. So here's kind of what that process looks like. So you're a user, you're in the browser, you go to Quantopian/research. QF is the Quantopian front end. So QF sends you, asks a request of this service that we call discovery to say, hey, is this user already associated with some running Jupyter hub? So it's just going to sort of make a regular SQL query to figure that information out. And the database might say, yeah, that user's on hub server 3, right? So the database sends that back to discovery. Discovery sends that back to QF. And QF sends a web page back to the browser that says, all right, I want you to render the Quantopian front end, and then inside of that, I want you to render hubserver3.quantopian.com. And now if I load that multiple times, this database can make sure that I get sent to the same hub, as long as that hub is still running. And it can keep track of the fact that that hub might go away, in which case when I make this request, it will allocate me to a new running hub. So just sort of some implementation notes about this. The discovery routing logic is super duper simple. There's probably fancy algorithms you could try to do to like route people based on their expected workloads or based on the resource usage on the server. We don't do any of that. We just say, we're going to put you on the hub with the least allocated users right now. One cool thing that we can do is we can subclass the Jupyter Hub built-in application class to do things like add additional logic when we initialize. So when our subclass starts up, it does whatever it would have done, and then it registers itself with this discovery service, and then it schedules a periodic callback to say, every second, just send a ping to that service saying, hey, I'm still alive. And that service is monitoring all those hubs and saying, all right, if any of them haven't sent a ping in enough amount of time, I'm going to stop routing users there. And if it goes even longer, I'm going to mark all those sessions as dead and reallocate people to different places. So that's what this heartbeating logic looks like. Also, the servers know themselves that if they fail heartbeats too many times, that they should just take themselves out of commission because they can't talk to the outside world. So they can say, all right, if I've failed too many consecutive heartbeats, I'm just going to bail out and gracefully shut down. So that's multiple hubs. One last thing that I wanted to talk about is sharing notebooks. So Quantopian, we talked a lot about research and talking a lot about developing algorithms, but Quantopian kind of first and foremost has always been a community of authors and researchers where people can share and talk about the different things that they're working on. So users need to be able to share and discuss the findings that they're doing in research. And we talked at the start of this talk about the fact that 90% of the work that you do that's sort of interesting is actually not in the development of the algorithms, is in the research that goes into the algorithms. And so what that means is that we need some format to be able to convey our sort of research findings to other users. And that's like the bread and butter use case for notebooks, where I want to do some interactive analysis, plot it, add some prose to it, add some context to it, build a narrative around it, and share it with other people in a way that they can understand and sort of incorporate into their work. So notebooks are this sort of ideal format for sharing the kind of exploratory research that we want people to do. And so the way that we do sharing and cloning is we use 2 more extension mechanisms that the notebook provides, which are NB extensions and server extensions. So NB extensions are additional pieces of code that you can add to the UI of the notebook, and server extensions are additional pieces of code that you can add to the back end of the notebook. So the sharing NB extension essentially just adds a little share button to each cell. And then what it does is when you click that button, it marks that cell as what we call a showcase cell. And that basically gets rendered as a preview as a user if you try to go clone a notebook. Because often you have sort of one nice concluding or cell or one sort of nice image that you want to show as a preview of your notebook, and get people to say, all right, is this interesting? Is this a notebook that I want to click on and explore? So it adds that to the metadata of the notebook and then sends a post with the notebook down to the server, which is where the server extension comes in. So the server extension adds a new request handler to deal with those posts. And that handler essentially receives a post that says, hey, user X wants to share this notebook. And the request handler does two things. So it uses nbconvert, which is a library that comes as part of the Jupyter ecosystem, to convert the notebook into HTML so that we can show people previews of the notebooks. And then it uploads the HTML and the .ipynb file to S3. And then the forums know how to sort of look in S3 for the right places for the notebooks and show them to people and show them previews. It can use the showcase cell to show them a little thumbnail preview. And then they can look at the full HTML to get the HTML preview. And then finally, they can actually clone the notebook and get a copy of the notebook that they can run and modify and edit on their own machine or on their own virtual machine. So some notes on sharing. The NB extension and server extension combo make it really easy to add arbitrarily powerful functionality to the notebook, right? So we can basically, theoretically, you could just rewrite the whole thing as an NB extension or a server extension. At some point, it stops being worthwhile if you're just deleting the whole thing and adding it as an extension. But you can sort of add as much logic as you want to into the notebook and then have the corresponding backend logic to make it work. Generally speaking, the server-side APIs, so sort of the pieces that are on the Python side, are more robust and stable. And if you've heard a bunch maybe about Jupyter Lab this week, that's part of the motivation behind that project, is to kind of stabilize and add more well-defined APIs for building these front-end extensions. So to wrap up, because I think I've only got about 1 or 2 minutes left. So Jupyter applications are these really amazingly extensible and customizable things, right? We talked about swapping out the storage mechanism for notebooks. We talked about adding mechanisms for sharing notebooks. We talked about swapping out the authentication mechanism for Jupyter Hub. And there's a whole laundry list of other extensions that I didn't have time to talk about. So adding tools for monitoring memory usage. We have a library called QGrid that gives you an interactive scrollable data frame widget. We've added custom completions. We've reworked the kernel restart logic to deal with some particularities of the way that we manage user isolation. We've subclassed the Docker spawner to add more custom rate limiting and resource limiting stuff. The list sort of goes on and on. Another conclusion is that state is the enemy of robustness and scalability, right? Lots of problems become way, way easier if we don't have to worry about state, or if we can at least delegate state to someone who's better at it than we are, right? So we can make our lives a lot easier scaling the hub by not storing state on the file system and instead storing in a database. And databases are really good at state. And then finally, Jupyter is built on a throne of lies, by which I mean appropriate use of indirection allows us to compose complex applications from single parts. Right? So we can provide the illusion of a simple system that you're just talking to directly while having sort of arbitrarily many hops between there, as long as we get the abstractions right. Couple special thanks. So I want to thank various members of the IPython and Jupyter team, without whom none of this work would have been possible. So Brian Ranger, Carol Willing, Kyle Kelly, Min Reagan Kelly, whole IPython Jupyter team, and then some Quantopian folks. So David Michaelowitz, Karen Rubin, Tim Shaver, who's in the audience, and the whole Quantopian engineering team. And with that, I think I am just about out of time. I don't know, how am I doing on time?
We can take 1 or 2 questions.
All right, I've got time for 1 or 2 questions before I go. You.
So we've got part of the file system permissions.
Yep.
Your Postgres table.
Yep.
Some of those columns, but how do those permissions work in your system? It's possible it's not.
Yeah, so we have, so the permissions aren't necessarily enforced in the file system, except the fact that they're namespaced by user IDs, right? So each user's notebook server basically only can see the files that are associated with its user ID, because part of the contents manager construction says which user's files am I managing. We could actually even go a step further with that. So Postgres has a notion of row-level permissioning, where you can say things like rows that match some SQL query can only be monitored by certain Postgres users. That would mean that we'd have to create a Postgres user per Quantopian user, which is why we haven't gone down that road yet. But if we got sort of very, very concerned about that, then that's a thing we could do. We also can enforce some amounts of security by the fact that we encrypt the notebooks at rest, and each user actually gets a different encryption key. So even if you could somehow, hack the notebook so that you could query for other people's files, they'd be useless gibberish for you unless you could figure out their encryption key. Over there. Our sharing model is basically sort of like publish clone. So I can take a notebook and publish it out to the community, and then a community member can come and take that notebook and clone it back to themselves. There isn't a notion of like collaborative sharing where like myself and a small number of coworkers, say, or of collaborators are working on a specific set of notebooks. So that's, sharing is kind of an overloaded term, and that's something we'd like to support in the future, but we don't have any kind of system for that right now.
How much of this is open source, and where can I learn more?
Yeah, so PG Contents is open source. It's quantopian.com/pgcontents. The authentication stuff, OAuthenticator is already open source and part of Jupyter. Most of the like libraries and systems that Quantopian is built on top of are open source. So Zipline is our open source backtesting framework. Trying to think what other technologies I talked about today. The sharing stuff is kind of inextricably tied up with our system, so that piece is not open source. Let's see if I pop back to the. Huh? The discovery layer is not open source, but that application is like pretty trivial. It's like users and servers, and there's like a relation between users and servers, and it's like a key value mapping. So that one's a pretty standard CRUD Python application. We probably could open source that if lots of people were interested in it.
All right, I think we'll stop there. Thanks, Scott.